I'm very excited for this. We're going to be continuing our journey with differential equations, but this time we're going to be going a power higher. So recall, first order differential equations, highest differential power is y prime, but now we're going to be dealing with y double primes, and that's going to be pretty fun. Okay, so let's talk about second order differential equations in this specific form. A double prime y plus b y prime plus cy is equal to 0. First of all, just a little warm up. What type of differential equation is this? And of course, it falls into many categories, but you can name a few, right? This is going to be linear, right? This is a linear differential equation. It's also homogeneous because, well, look what's on the right hand side. It's going to be equal to 0, right? And of course, it's second order. And so what we're going to do is, in order to solve this equation, I'm going to use a very, very handy trick. And I'm going to take advantage of the fact that the derivative of e to the x is equal to e to the x. And the derivative of e to, let's say, some power, so derivative of e to, let's say, rx, the derivative of e to the rx is just going to be r times e to the rx. This is the thing that I'm going to be taking advantage of when I'm going to be trying to solve this equation. Okay? Now, let's assume, all right, I'm going to make a little assumption here, okay? We're going to assume that the solution to this equation is going to be equal to, I'm going to assume the solution to this equation is going to be y is equal to e to the rx. Okay, that's my assumption. Well, that means that y prime is equal to r times e to the rx. And that means that y double prime is equal to r squared times e to the rx, or to the rx power, sorry. And so let's plug everything into our equation. So by making this initial assumption about our solution, now we're able to, instead of dealing with these higher power derivatives, we're actually able to compute the higher power derivatives because we know what they are, right? We made that assumption already. And so when we substituted everything in here, we're going to get a times r e to the rx plus b, we know y prime, that's going to be r e to the rx. There's going to be a lot of e's in this video. And then we know that c multiplied by y, well, y is just e to the rx, right? Sorry. And that's going to be equal to 0. Is there any common terms that I see here? Let's factor out a e to rx, right? Because I noticed that in all my terms here, I have an e to the rx, right? So if I factor e to the rx out, I get e to the rx times, I'm just going to be left with ar squared plus br plus c. And all of that's going to be equal to 0. Now, think about it. If you have e to some power, can it ever be equal to 0? Think about it. Right? If I have something like e to the 2x, can that ever reach 0? It can get closer and closer, like a horizontal asymptote to 0, but it never actually reaches 0. This is just rounding down because the calculator isn't precise enough, but you can see that we're getting closer and closer to 0, but we don't never actually reach it. So we know that this term right over here, this e to the rx term, it can never be equal to 0, right? So you gotta just ignore that. But we know that this polynomial that I have right in here, that can be equal to 0. And we're first going to be dealing with real solutions of this polynomial, in which, it's going to be very nice. But then we're actually going to move on to solving for complex solutions, which is just using the quadratic formula or, other, types of methods like completing the square, whatever you want to do. But the point is here that we've essentially turned our scary looking, differential equation second order into a polynomial because we're assuming the solution to this equation is in a specific form. And this is a very, very powerful trick, okay? So let's actually do an example. Enough talking with variables, and let's actually move on to an example. So I'm going to move here. And let's say that I have, I don't know, y double prime minus y prime minus 6y. Let's say that's equal to 0. Okay? So when we start out with an initial differential equation like this, we can actually convert it into this form. So what is it going to look like? This is just going to become e to the rx multiplied by, what is a? A is the coefficient here, which is 1. So 1 times r squared plus b, well, b is just the coefficient here, which is just -1, right? So it's just minus, r, right? Minus r. And then plus c, well, what is c? C is the coefficient of this right over here. And so that's just going to be -6. And we set all of that equal to 0, right? And so, the kind of trick to doing this is you only need to look at the coefficients, and then you're able to write out this quadratic equation. And so we kind of ignore this e to the rx because it has no solution for that. And this just becomes an easy factoring problem, right? R minus 3, it looks like, times r plus 2. That is going to be equal to 0, and therefore r is equal to 3, and r is also equal to -2. Now, what do we say? We said that we assumed that the solution to this equation is going to be in the form of y is equal to e to the rx, right? Remember, that's originally where we kind of came from. And so now that we solve for r, all we have to do is just plug that into our equation. So we have two solutions, right? I'm just going to call this y1 is equal to e to the 3x, right? Because 3, just substitute it in here. And y2 is equal to e to the -2x, right? Because you just plug in -2 in for r. Okay. And of course, we can't forget the constant. Okay. And the thing is that there's actually going to be two constants. You can think about it as there's some sort of mysterious constant in the front of our first solution, and there's some mysterious constant in front of our second solution. All right. And I actually didn't include this in the start because I was trying to make things simple. But the thing is, you can also, you can kind of assume the solution has the form c1, some constant, times e to the rx. And that means that y prime is r e to the rx times c1, right? Just multiply it by c1. And then y double prime is r squared e to the rx times c1, right? Notice how this is just a constant multiple, meaning that using the derivative rule, we kind of just leave that alone. And so when we actually, plug in everything, you're able to see that all these terms have c1. You're able to factor it out of there. And so the form that you end up with is c1 times e to the rx. And so therefore, we're able to add an arbitrary constant to the front. And these constants are, they're going to be different. And these constants right over here, they're different constants. All right, because we end up with two solutions, okay? Now, it turns out that we can actually combine this into one solution. And we can kind of say that the overall solution, I'm just going to call it the overall solution, is just actually going to be the sum of these two solutions. So my overall solution is going to be c1 times e to the 3x. So it's going to be c1 times e to the 3x. And it's just going to be plus c2 times e to the -2x. So to find an overall solution for these types of equations, when you get real solutions, like, what we have here, the overall solution, you're just going to add it up, okay? Let's just plug everything back into, our original differential equation, and let's see what we get, okay? So plugging the first differential equation into our solution, or into the equation, well, what is y prime? I know that y prime is equal to 3 times c1 e to 3x, and y double prime is going to be equal to 9 times c1 e to 3x, okay? And so if I plug both these back into my original equation, I get 9c1 e to the 3x, and then this is going to be minus y prime, which is just 3c1 e to the 3x, minus 6 times y. Well, what is y? Y is c1 times e to the 3x is equal to 0. And notice how all these cancel out to be equal to 0. Okay. Now, likewise, I would also get 0. So I know that if I plug everything in y1 into my differential equation, I'm going to get 0. And if I plug everything from y2 into my differential equation, I also get 0. So because the derivative of the sum is just the sum of the derivative, well, then this is basically, if we add these solutions together, I'm essentially just going to get 0 plus 0, right? If I actually plug everything back into the original differential equation. And because we're dealing with homogeneous differential equations where the other side is equal to 0, 0 plus 0 is always going to just equal to 0. Now, for secondary differential equations, well, we need some initial conditions. So let's go back to another example. Let's say we have y double prime plus, let's do something weird. So we know that it's going to involve y double prime, y prime, and just regular old y. And let's say that this is equal to this. So how do we do this? Recall the formula, right? It's going to be r squared, ar squared plus br plus c is equal to 0. So a quadratic equation where a, b, and c are essentially the coefficients here. And so we essentially have r squared plus 6r plus 8 is equal to 0. And that means that r plus 4 times r minus 2 times r minus 2 is going to be a factor, okay? Or sorry, r plus 4, r plus 2. Sorry about that. And so what we can do is we can say that r is equal to -4 and -2. Okay? And so we know that the general solutions for this, so this general solution is going to be y is equal to, and we can combine these two solutions, right? So it's going to be c1 times e to the -4x plus c2 times e to the -2x. But what if we were trying to solve for this constant? So let's say we're given that, we're given f of 0, let's say that's equal to 3. And let's say that we were also given that f prime of 0 is equal to 2. How can we solve for these constants? Notice how for second order differential equation, you need two kind of initial conditions, right? You need the regular old function value, and then you need its derivative. And we can think about these as degrees of freedom, which I'm just gonna abbreviate as df. But in order to solve this differential equation for the two constants, you need two initial values. That's actually another reason why we need these two constants, all right? So these 2 degrees of freedom match up with these two constants that we get with our equation. And this is going to be really important later on, so keep this in the back of your head. But once again, this is just another plug and chug, like what we kind of did with differential equations first order. And so recall that whatever you put inside the function, that's your x value, and then the corresponding output's the y value. So we can say that 3 is equal to, and when we plug in 0 into this, well, e to the 0 is 1, so I'm just going to be left with c1 plus, and once again, e to the 0 is 1, so 3 is equal to c1 plus c2. Now, we're also given that f prime of 0 is equal to 2. So what is the derivative of this entire thing? And so I actually took the derivative of this, and so I got that y. So I actually differentiated this, and I got that y prime was equal to, well, you kind of just drop the power, I guess you can say. So -4 times c1 e to the -4x minus 2 times c2 e to the -2x. And because our initial f prime condition is when x is equal to 2, or sorry, x is equal to 0, I plug in 0 into this, I'm just going to be left with -4 times c1 minus 2 times c2. And notice how we have a system of linear equations here. So we can just solve for c1 and c2. So let's go ahead and do this. Hopefully I remember how to do this. So c1 is equal to 3 minus c2. We could plug c1 into this. So I get that 2 is equal to -4 times 3 minus c2 minus 2c2. And so we get that 2 is equal to -12. And negative makes a positive 4c2 minus 2c2. Great. Those two things create 2c2. And then so if I move this to the other side, I get that c2 is equal to 7, right? Okay. And so I know that if c2 is equal to 7, then 3 minus 7 is equal to -4. And those are initial conditions. Then I just place them back into my original solution. So c1 would just be equal to -4 right over here, and c2 would just be 7 right over here. And so with higher order differential equations, all you just have to do is solve system linear equations because you're just given more initial conditions. So we kind of covered the first case, right? Think about the cases for a quadratic equation. You can either have two distinct roots, two distinct real roots. You can either have that, a double real root, or the scenario we're going to cover next, which is complex roots after this. You might think that, well, okay, the solution is very easy. It's going to be c1 times e to the negative 3x plus c2 times e to the negative 3x. Whoa, wait a minute, there's a problem here. These are both constants, right? So imagine if constant 1 was like 3 e to the negative 3x and constant 2 was like 5 e to the negative 3x. Notice how then you can combine these like terms, right? And this just becomes one e term, right? So c1, if I wrote the solution like this would just converge to kind of like a big constant times e to the negative 3x. And of course, we don't want this, right? Remember how we said how this second order differential equation, since we have kind of two initial conditions, we kind of need to have these two constants, right? These two constants as our solution. And so the problem here that we're encountering is that, well, we can't kind of use our general form to write it out because this is a constant 1, constant 2, same form, you can just combine it. And so what do we do here? It turns out that this first term right over here, we can keep it as is. But the second term, we have to do something about it. And the thing that we actually have to do is we actually have to put a little something something there. A little x. All right, so we multiply this by x. And this is actually the equation to the secondary differential equation. So when we're dealing with a double real root, you kind of keep the first term the same, and the second term, you kind of write it out as is, but you just multiply it by x. This x is serving a very important purpose. It's making sure that you can't actually combine these two terms so that, it turns into like a big constant, if you will. Now, the reason why this actually works, so this isn't going to be like a formal proof or anything, and if you haven't really learned linear algebra yet, then we can kind of skip to the next part. But this is actually something related. This is something called the Wronskian matrix. My pronunciation is very bad. Wronskian matrix. I like to pronounce it like that because why not? And this is just going to be a matrix where you're essentially going to have your first solution, right? And the derivative of the first solution, and then your second solution, and then the derivative of the second solution. And what you're going to do is, if you take the determinant of this matrix, and this is not equal to 0, then that means that your solutions are going to be independent of each other. Independent of each other. And if it is equal to 0, then it's going to be dependent. So I know that's kind of a random throw kind of at your face of, just some random matrix, but let's try to make sense of why this matrix is used and why we can actually put an x in front. I'm not going to get too formal into this, but you can think about this as like a vector, right? So this first vector that we have right over here is our first solution and the derivative of the first solution. And the second one is going to be our second solution and the derivative of the second solution. And so you can think about these two vectors, right, on, let's say, some coordinate plane out there, and they kind of represent the solutions, right? And so if I draw them out, right, let's say that this is going to be let's just say this is going to be my vector 1, and let's just say that this is going to be my vector 2, okay? Now, if the determinant is not equal to 0, we can say that these two vectors are independent. And recall what the determinant does, right? It kind of measures the area of this parallelogram. It kind of just measures this area of the parallelogram that these two vectors form. All right? And so if the vectors are kind of diverging away from each other, then we know that these solutions, they have to be independent of each other, right? They're kind of going in different directions, which is good, right? Because we want these two constants to be, completely different sort of terms, completely different kind of solution sets, if you will. All right. But if these two vectors are scalar multiples of each other, you can think about it as if these two vectors are kind of just like multiples of each other. So this right over here would be V2. Notice how they don't really form a parallelogram. They don't form a parallelogram at all. And so the area of the parallelogram that they form it's just going to be 0, right? They are not forming a parallelogram. It has an area of 0. And so that means that these two kind of solutions right over here, they're representing the same multiple, right? The same kind of situation where we had before, where without this x, they are just going to merge into like one big constant, and it's just going to represent the same thing, right? And so that's kind of like a kind of informal representation of why we compute the determinant of this matrix. It's because we want to see these solution sets kind of diverge, and we don't want to see them kind of facing the same direction as a scalar multiple, because otherwise they're just representing the same solutions. Okay. All right. I know that was a lot. Let's calm ourselves down with a little bit of complex numbers. And one thing you got to know beforehand, and this might just be like prior knowledge stuff. Or sorry, I don't know. I don't even know how I did that. How did I do that? So all of a sudden, this thing's back. Okay. So one thing that you got to know beforehand is that e to the ix, or I'll say e to the I theta, is equal to cosine of theta plus I sine theta. All right. This is what you kind of need to know beforehand. And so let's get on to it. All right. Let's say if we have a differential equation. So a double prime y plus b prime, b times y prime plus c times y is equal to 0. And let's say that after we solved this equation, we get that r, remember that y is equal to some constant times e to the rx. Let's say that we have r being equal to a plus bi, or a plus or minus bi, because remember that this is a quadratic equation at the end of the day, so whatever complex number that we get, we're also going to get the conjugate of that complex number, right? Because it comes in pairs. And so how can we write out a general solution for this? Okay, so we know that one solution, I guess we can call this y1, is equal to c1 times e to the rx. And so one rx that we can have is a plus bi times x. And then the second solution that we get is this right over here, where our exponent is just going to be a minus by, right? It comes straight just from our r value. One is going to be plus, the other is going to be minus. And so recall that the overall equation is just going to be, well, the sum of these two equations. Just copy, paste. Yes, this does generalize for complex numbers. That's the cool thing about this. Okay, so let me just copy and paste the second one. Copy, paste. That was pretty bad. Let's try this again. Copy, paste. Yes. Honestly, the next part is just going to be some exponential rules. Okay, so y is equal to c1 times e to the ax times e to the bix. Bix, right? Because this is just due to, exponent properties, and then that's going to be plus c2 e to the ax, and then times e to the negative bix. And so we can factor out an e to the ax from both terms, right? So it looks like I can factor out this e to the ax term in the front, and so I'm just going to be left with c1 times e to the bix plus c2 times e to the negative bix. Okay. Sorry, guys. I should probably, maybe to make it clear, I'll put ibx. Okay. So instead of bix right over here, I have e to the I times bx, and then this is going to be negative I, and then times bx, right? Now call back to this form right over here. E to the I theta is equal to cosine of theta plus I sine theta. So I can actually expand these two things out, okay? So this is just going to be equal to, well, my first term is going to be equal to, well, e to the I, or sorry, cosine. Sorry. Switch to another color. The inside portion right over here is going to be cosine of, well, in this case, my theta term right over here well, we can think about I as corresponding to this I, and that means that theta has to correspond with this bx right over here. So cosine of bx plus I sine of bx. And then likewise, for this C2 portion right over here, and I'm also going to put another bracket, it's going to be the exact same thing, except instead of just regular old Ix, or sorry, instead of just regular old Bx as the angle, right, instead of theta, we have negative Bx, right? So I corresponds with I, and then theta is represented by negative Bx, right? That's how they're equal to each other. And so we get cosine of negative Bx, which, cosine's due to cosine even function properties, cosine of a negative, so cosine of an angle is equal to cosine of the negative of that angle. So therefore, I can just write this as Bx, right? Cosine is just positive Bx. And this is going to be minus I sine of Bx. Once again, I can move the negative from that I negative Bx to the front because sine is an odd function, right? And I close this out with parentheses. So I can do another bit of factoring right over here because notice how cosine of Bx, they're both shared by these two constants. So I can say that this is equal to, I can say cosine, or sorry, we just do this in a different color. So both C1 and C2, I can see that both C1 and C2, they both share this cosine of Bx term, right? And I can actually likewise factor it out, right? I can actually factor it out for this I sine of Bx term as well, because, well, if I factor out negative from here, and then I just factor out I sine Bx normally here, what I would actually get is in parentheses, right? And then so we want to have regular C1, and then instead of plus C2, we have minus C2, right? Because we have to put a minus sign right over here because we're trying to kind of get rid of the negative, if you will, right? In order to make this positive. So we're actually able to factor out that I sine of Bx term, right? Okay. Notice how C1 plus C2, that's just going to be another constant, right? Which I can just call A, or A1. And notice how C1 minus C2 times I, this right over here, is also just going to be another constant, which I can call A2. Therefore, the general solution for complex second order differential equation is just going to be some constant A1 times cosine of Bx plus some constant A2 times sine of Bx. Remember that the I gets absorbed into this constant. And all of this is going to be multiplied by e to the ax, where a is the real part of the complex number. And so this is going to be the general form, okay? The thing is, once you have this form recognized, you don't have to do any of that annoying algebra again, right? And all you have to do is just plug and chug into that formula once you have found the roots. So the most that you need to do for these types of equations is kind of just to memorize this algebraic form and to also know how to do the quadratic formula. And so if we were to solve this, right, remember this is r squared plus 2r plus 5 is equal to 0. Let's actually complete the square, all right, because we have an even number here. So we have r squared plus 2r. I can move the 5 to the other side, and I can add 1 to both sides, looks like. So it's just going to be -2, or -4, and then this is just going to be r plus 1 squared is equal to -4. I square root both sides, and I get that 2i is going to be equal to r plus 1 plus or minus 2i, right? Because remember, when we're square rooting, we have to add the plus or minus. So plus or minus 2i is equal to r plus 1. And that means that r is equal to -1 plus or minus 2i, okay? And so what do we have to do now? We just have to plug this all the way back into our equation. And guess what? It's right up here. So let me actually move this all the way up here. It's actually very, very simple to do. What do we have to do? We have to let a be equal to -1. So this is just y is equal to e to the -1x, or just negative x, times the first constant times cosine of bx. And remember, b is right over here, right? This is represents b. So this is going to be cosine of 2x plus the second constant, a2, times sine of 2x. And then we're just going to be done. This is the solution, okay? Nothing more than that. And so the good thing about these constants is that, you know, this a2, a1 and this a2 account for the other constants that we have encountered earlier with the c constants. The a constants absorb those. So that's very nice.